All right, so today we are going to be learning about waves. And we're going to learn about waves by adding 7 items to our physics everything sheet. So just to refresh your memory, your physics everything sheet is on the back side of your core tools packet. Flip onto the back side, there it is. You've already filled in the first probably page or two, probably 2 pages. So now we're ready to move on to your 3rd page or even your 4th, wherever you're at, and just keep adding. Okay, so pull that out and let's add. Okay, so we're going to start with 2 different definitions of a wave. It's 2 different models of a wave. A wave is a way that energy is transferred through a medium. So we have 2 types of waves. They're called transverse waves and longitudinal waves. A transverse wave, and we're just going to start with the concept, no variables for these, they're just 2 definitions. A transverse wave is when the particle motion is perpendicular to the direction of the wave motion. So the wave motion, the energy is being transferred this way, and the particles are moving up and down as the energy is being transferred through. So energy going through, particles go up and down as they go across. An example of this might be something like an ocean wave, where the ocean goes up and down, that makes a wave, as the energy goes through the water that way. So perpendicular means at a right angle. As the energy goes horizontally, the particles move up and down. That's at a right angle. This is called a transverse wave because the root word trans means across. So the particles are going across the median line. They're moving up and down, crossing that middle line over and over again. So remember, trans, across. So they're going backwards and forth, up and down the median. All right. A longitudinal wave is our other option. And a longitudinal wave is when the particles move along longitudinal along the direction of the energy. So the particles are going to compress and rarefy. Compress means get closer together. Rarefy means get further apart as the wave energy moves along. That is parallel with the particle motion. So the particle motion is this way. The wave energy is also this way. So wave energy, particle motion. So it looks something like this, zoom, 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 as they're getting compressed and rarefied in the same direction as the energy. All right, let's take a look at a couple pictures. I'm going to start with images and pictures here, diagrams. Okay, so for a transverse wave, this one over here is transverse because it's crossing the midline. The energy is transferring horizontally here along this blue line. So the wave energy is going horizontally, and then the particles are going up and down. This leads us to this big swirly line. It's a sine wave. So if you're familiar with trigonometry at all, sine waves are examples of a transverse wave. And we're going to use that as our primary model. The other option is the longitudinal wave. That's a compression and a rarefaction wave. So I'm representing my particles with these vertical lines, like these guys. And a compression is where they're all tightly packed together. A rarefaction is where they're more spread apart. They're rarefied. So I have areas of compression and rarefaction. And then you'll notice that I could measure a wavelength from the middle of one compression to the middle of the next compression, or I could do the same thing from the middle of a rarefaction to the middle of the next rarefaction. All right, details. In terms of notes, for both types of waves, it is a model of how energy is transferred. Okay, so both types of waves are a model of how energy is transferred. Other things to note. On the transverse wave, the transverse up and down one, an example of that would be light. Light is a transverse wave and everything on the electromagnetic spectrum. So that would be radio waves, X-rays, microwaves, ultraviolet light and radiation. That would all be part of the electromagnetic spectrum, and those are transverse waves. One of the neat things with transverse waves is that they don't require a medium. So there is no medium required, meaning there doesn't have to be any stuff to go through. A light or an electromagnetic wave, a transverse wave, can travel through a vacuum. So there doesn't need to be any molecules to move that wave or move that energy through. All right. The other type, longitudinal, an example of a longitudinal wave is sound. Sound is a compression and a rarefaction. That's why sometimes you can like feel sound. If you put your hand up against a speaker, you can like feel it thumping. In fact, let's do that right now. Put your hand up against your throat and go, ah, and you can feel your throat vibrating. Your vocal cords there are vibrating back and forth really fast, and that's what's creating the sound waves. So sound does need a medium. It needs some stuff. And the reason that it needs a medium is because it's a compression and a rarefaction. You have to compress something. You can't compress and rarefy if there are no molecules to compress and rarefy. So you have to have a medium for a sound wave or a longitudinal wave. Other notes is in terms of what medium, sound will go faster in a solid, and actually it's based off of the stiffness. So if an object is really stiff or rigid, then the wave speed will be faster. So a really stiff or a really rigid material, so that'd be like aluminum is really stiff or rigid, something that is not easily bendable. Okay? So water would be really not rigid. Air is super not rigid. Look, I move my hand around and it just gets out of the way. So air would not, the speed of sound in air is pretty slow compared with the speed of sound through, say, like a metal piece. Okay, now let's get to some other pieces. So now we're going to add 5 different factors that all have to do with waves. Okay, so the first one is wave speed. We're going to use variable v for velocity, and that stands for wave speed. And wave speed is how fast a wave travels. It's wave's velocity. The equation that we're going to use is that the wave speed is equal to the wavelength times the frequency. V equals, it's a lambda, which will make more sense when we discuss wavelength in just a second. And because it's a speed or a velocity, the unit is going to be meters per second, m over s. So notes about wave speed. We just mentioned that the speed is going to be faster if it's stiff or rigid, but most of the time we're going to be dealing with sound in air. So the speed of sound at room temperature in air is about 340 meters per second, which is about 760 miles per hour. That varies slightly based on temperature and elevation. But generally, we'll say that for our purposes, the speed of sound is 340 meters per second or 343 meters per second, but somewhere in that range. How would I diagram this? I'm drawing my wave, and it's a wave speed. So I'm drawing this big arrow, like that. Fast speed going in that direction. Okay? How fast is the wave moving sideways? And that's the energy that's moving. All right. Next piece is wavelength. So wavelength, we're going to use the variable lambda. Lambda is the Greek letter L, and it's like an upside down lowercase y. Okay, so there's lambda, L for length. So this is the wavelength. And the wavelength is the distance of one wave, either from crest to crest, so that's from the top of the wave to the top of the next wave, or from trough to trough, or from compression to compression, or from rarefaction to rarefaction. It's the distance of one complete wave. Our equation here is just a manipulation of the previous equation, V equals wavelength times frequency. So now I've solved for wavelength, and that gives me the lambda wavelength is equal to the wave speed divided by the frequency. The unit is meters because it is a length. And then if I was drawing it, I drew my wave. One wavelength would be from crest to crest, so from right here all the way over to right there, or from trough to trough, so that's from the very bottom of the wave to the bottom of the next wave, or I could even draw it from midpoint to midpoint as long as I chose the same types of midpoints. So if I go midpoint right here on the way down to the next on the way down midpoint is right there. So that would also be one wavelength. So I could also say that is a wavelength. And then I've also drawn a wavelength up on my compression rarefaction longitudinal wave. So that would be from compression to compression. It's the same idea. It's just here I've represented it as high point to high point. And here I've represented it as dense higher pressure point to higher pressure point, compression to compression. All right. Next, we have frequency. For frequency, we're going to use lowercase f. The frequency is the number of vibrations or the number of waves per second. Right? Number of vibrations or waves per second. The unit, or let's say the equation for that, again, it's a manipulation. Frequency is wave speed divided by wavelength. Or another one that I could put in here is that the frequency is 1 over the period, if you have a period. T is going to be period. The unit here is waves per second because it's the number of waves in a unit of time. So waves per second, or I can use 1 over seconds, and that actually has a special name, and we call it hertz. HZ stands for hertz, capital H, lowercase z. And so the unit there is hertz, and no real notes or diagram. Next, we go to period. Period, we're going to use T, capital T, because period is a unit of time. The period is the amount of time per wave, or the time per vibration cycle. For every back and forth vibration, that would be 1 period. Our equation for period is that period is 1 over the frequency. Because remember, frequency was waves per second, period is seconds per wave. So the unit there, because it is a unit of time, would be seconds. So the period would be measured in seconds. And then finally, our last piece to add is going to be capital A, which represents amplitude. And the amplitude is the height of the wave. So it is the distance from the midpoint of the wave to the maximum point of the wave. So the distance from the midpoint or the midline up to the maximum. I'm not really going to give an equation for this one, but I am going to note that intensity is directly proportional to amplitude of the wave squared. So if you take the amplitude of the wave and square it, that would give you a measure of how intense that wave energy is. Because it's a distance or a height, we would represent it in, or use the unit of meters, m. And amplitude would control the volume of sound. So wavelength and frequency control the pitch, like high, low, and amplitude controls the volume of the sound, like loud, soft, quiet, quiet, loud, quiet. There you go, same tone, but different volumes. All right, so in terms of showing that, the amplitude would be from the midline there, all the way up to the top, and then all the way down to the bottom, right? So that would be 1 amplitude is just from the mid down to the bottom. Okay? So there's your amplitude. All right, so that is 7 new items for your physics everything sheet. And now we're gonna be using them a lot. So as you use all of these, we're gonna do a lab and start kind of putting them into process. Great job. Look forward to doing more wave work with you in just a second.